Hello, so in this video we're going to delve deeper into logarithms and we're going to look at something called laws of logarithms. So firstly, as a recap from last time, we saw that a logarithm, the whole idea was if you have a base a to the power of x equals b, right? It equals something. Then what we said was as a logarithm, so we use these double lines, double arrows means equivalent, right? So this is equivalent to the equation log base a of b equals to x. And so what a logarithm tells me is it tells me the power, okay, the original power, okay, in my exponential. So for example, if we had 2 to the x, let's say equals 8, well, we know that 8 is 2 cubed, so therefore x, the power x is 3. So as a logarithm, we would say log, the base is 2, right, the base number 2 of 8, because it equals 8, and so that gets me in the power of 3, okay? Right, and so before we look any deeper, I want to scrutinize kind of exactly when we use logs. So I'm talking about like the domain and stuff like that, right? To do this then, we see that the log has a base part and an input part, right? An input part b, right? So it has a and b, so we need to scrutinize when a and b, what values they could be. Because you can't just put any number in. There are certain restrictions we need to put on these values. So firstly a, right? So a is my base, right? So actually, if you just look at the base, we don't look at the logarithm equation. Let's just look at the exponential. Well, we can take any value of a that's greater than 0, right? A has to be positive, has to be above 0. That is because if a was less than 0, firstly, well, what would happen is it would be negative, right? So you'd have something like -1, and then x could be anything, right? Let's say x is 3/2. The problem here is you'd have to, because it's a fractional indice, because then we could say that's -1 to a half, then cubed. Well, this -1 to a half is a root. I'd have root -1 cubed. But the problem is, that's a negative and a square root. That's undefined, right? As we know it. So what happens is exponentials can't work when we have a negative value of a. Okay. So because of that, a, the base a, my logarithm has to be positive. Firstly. Okay, so a cannot be less than 0. Right? A cannot be less than 0. But what about if a equals 0? Well, then we would have 0 to the x, right? That's the exponential. Well, you might think, man, that just equals 0, right? But the problem is that's not valid for all x because, well, think about it again. If x was negative, let's say 0 to the -1, that'd be a reciprocal, right? 1/0. Well, hang on, we can't divide by negative, and so that cannot work either, right? Or -2 or -3, you would have to do a reciprocal, right? So actually, for all values of x, a cannot be 0, okay? Or else the exponential will break down, as you just saw. We're then divided by negative, which means the logarithm won't always work either, right? So that means, because a cannot be less than 0, as we saw, or it cannot be equal to 0, a can only be positive, right? Okay, also there's another one where a, specifically with logs, a also cannot be 1. That is because, well, if a was 1, then we would have 1 to the x, right? Now actually you might think, well, it's equal to 1, right? 1 to the power of anything is 1, and that also works with like negatives and stuff like that. Like -1, that's just 1/1 if you do the reciprocal, which is 1. That's all fine. That is defined. 1 to the power of anything is 1. but it's not an issue of whether it's defined. What the issue is actually if we were to convert this into a log now, right? We'll say that the log of base 1 of what we get 1 is equal to x, right? The problem here is we need a unit. We can. There should only be a single value of x that satisfies this, because 1 to the power of anything is always 1. X can be absolutely anything. So it could be 1. It could be 2. It could be 3. It could be absolutely any value whatsoever. There's not one single value that satisfies this logarithm. And you'll see in year 2 that there should always be, for because in order for it to be a function, we must only have one single value possible out of a function. There should only be one possible output. The fact of the matter is, if we take log 1, right, log to 1, if we evaluate this, there'll be infinite solutions, because you can basically, what this means is I can have any power of x at all. I only want one power of x possible, right? So actually with logs, because we only want we want the function to work, which means it needs to give one single output, not many. A cannot be 1 either. Okay, and that's it. That is the domain of x. So remember, the domain is the possible outputs. Okay, so that means A has to be positive but also not 1. Okay, usually they're not that. I've not seen exam questions usually, but you need to basically know that whole domain, but it's still good to go over, right? You still do need to know it, but that is the restriction on the possible values of A. Okay, that's the domain of A. Now what about B? What about our input B? So, well, actually, we can look at the logarithm again, the exponential again. So the values of B we can put into a log, right? So we discussed the A, so now B. Well, actually, A to the x, right? We saw in exponentials that A to the x has 2 possible graphs, right? One graph is it increases when A to the x, right? That increases when A is above 1, and also the other possible graph is it instead goes the other way. It decreases. It decreases instead if A is between 0 and 1. Okay. So these are my 2 possible graphs of A to the x for any base A, right? What do you notice, so that in general, either graph is above 0, right? They're all positive. So A to the x is always positive, it's above 0. Well, A to the x equals B. So that means B is always 0, and that's it. Okay, so with our logarithm, B, our input B, you can only have inputs that are above 0, okay? If you were to put in, let's say, log of 2 to the 0, you would get undefined, okay? Or if you do log 2 of, let's say, -3, it's a negative, that would still be undefined. If you have log of, let's say A is 0 now, of, let's say, 3, that would still be undefined, okay? So what I'm saying here is these are the only valid values for A and B, my base A and my input B, my log, okay? If you put values that are not outside of this, if you put any values of A or B outside of these values, you'll get an undefined log, okay? This is the domain of the log, so I'm going to get rid of all this. This is the domain of a logarithm of log A to the base A to B, okay? You need to make sure, but again, as I said, they don't usually test that, but again, you need to know, but you need to make sure when you input in a log that the values of A and B, these conditions, are satisfied. So generally with A, you want A to be positive but not 1, and with B you want my input to be positive. Okay, so generally positive all around, right? So generally, to summarize it, you want my values of A and B, my base A, my input B, in my log, to both be positive quantities. Okay, so I've got that out of the way. Let's have a look now at log laws. So with when we look even at GCSE, but at the start of the course, in the first chapter, we saw exponential laws, power laws, right? If you remember, we had the A to the base m, and then we multiply it by the same base A with a different power n, and remember we can add the powers, right? That was my first one. My second one was if I divided instead, and so we subtract the powers. And my third one is this. So we have A to the power m, but this is all raised by a different power n. We could just multiply the indices, right? Now, why am I bringing this up? Well, we can actually find out logarithm laws in the same sort of way, because logarithms are equivalent to an exponential, but we know these exponential laws, so we can use this to find in logarithm laws as well. So let's firstly work with this one. Okay, a to the m, a to the n is a to the m add n. So what we can do is actually we can say that a to the m is a number p, right? And then and also a to the n is q, right? Two different numbers. Now actually we know how to convert these back into logs now, right? So if we convert this as a log, then that'd be a log of the base a of p equals m. And we also, if we convert this bit into a log, okay, but also we know that if we times them together, a to the m times a to the n, we'll get a to the m add n, right? But if we multiply them together, remember a to the m is p and a to the n is q. What we're saying is that a to the m add n is pq, right? So a to the m add n is pq, p multiplied by q, because that's a to the m, which is p, multiplied by a to the n, which is q, right? So hopefully you can see that, right? So I got to this statement, and now I can take logs, right? So if I convert that into a log, then the log of my base a of pq is equal to m add n. Well, hang on, what is m? This is m here, and this is n here. So what we can therefore deduce is that log, that m add n, which is log a of p, and log a of q is equal to log a of pq. And this is my first logarithm law, okay? But basically what this is saying is if we add two different logs together, we can combine them and multiply them in one, okay? So that's my first one. Now the second one we're going to prove is going to be based on the second power law, right? So now if we say, what we're going to consider is this, where a to the m divided by a to the n is a to the m minus n, right? So again, what we're going to consider is, we're going to say that a to the m is again going to be p, and a to the n is some number q, right? And so what we can say then, we could take logs to say that log of base a of p is equal to m, and here log of base a to q is equal to n, okay? So again, remember my logs give me my power. So what we're going to do then is divide. So I also know that also if I do a to the m divided by a to the n, that's a to the m minus n. But if I'm dividing a to the m of a to the n, remember that's the same as a to the m, which is p. So I'm doing p divided by q, because that's a to the n. So what I can say is a to the m minus n is equal to P over Q. And then if I take logs again, I convert that into a log. That's log of base A of P over Q is equal to M minus N. And so then lastly, I know that M and N are these two logs up here. So I can say that therefore log of M, which is log A of P, take away log A of Q, so that's N, right? If I take them two away, I get log A of P over Q. Okay? And that's my second power law. Okay, so it's kind of similar to the first one, where instead of adding two logarithms, we take two logarithms away, then we can bring them as one log and divide them. Okay, that's my second one. My third one is going to be then based on the third power law, right? This power law here. So I'm going to remind you, it's A to the M of base N. And then again, we can multiply the powers. So that's my power law, right? So I want, if I'm going to consider a logarithm, well, what we can do firstly is, well, this A to the M again, A to the M, I'm going to again call P. So then, but also we know that if we raise A to the M to the power of N, that's A to the Mn, right? But A to the M is P. So that's P, that's also equal to P to the N. So therefore A to the Mn is P to the N. And so then if we can take logs, then log of base A of P to the N, right, that's what it equals to. That's going to equal my power Mn. But we also know that M is this log here. So therefore we can say that log A to the Pn is M. Well, I'm gonna rearrange it ever so slightly to Nm. Okay, you'll see why. Because then that's N, lots of M. But we know M is this. So it's log N log A of P. And there's my third one. And so what this is saying is, if we have a power in the log, so if we have some P to a power N, we can effectively bring the power to the front of the logarithm. Okay, so you can see that N is outside the log here. Okay, so that's that. So that's my third one. And those are the main ones, really. We can prove a fourth one by using the power law, that we know that anything to the power of 0 is 1, right? So if we use that, then simply that would mean that if we take a log, that'd be log base A of 1 is equal to 0. That's my fourth one. That's saying that effectively, if you have any base A, any log whatsoever, if we put 1 in, we always get 0. That's my fourth one. My fifth one is, well, A to the power of 1 instead of 0, that will always equal A, right? A, anything to the power 1 is just itself. So if we take a log of that, log base A, which is equal to A, gets me my power 1. Okay? And that's my fifth one. Okay? Okay, fairly simple, the last two. But these 5 equations make up my power laws, right? So if I restate it, my first one effectively was log A to the P, add log A to a different number Q, 2 different logs. We can bring them and into one log and multiply them of base A. Okay? My second one was, if I subtract, so if I do log A of P, take away log A of Q, I can then bring them as one log again, but I divide them, P divided by Q. My third one was log A to P, but that's to a power N. I can bring the N outside the log. And my fourth one and my fifth one of these So log, I'm gonna do the fifth one first. So log a of a equals 1 and log a of 1 equals 0. These are my 5 log laws which you do need to remember. You do not need to know the derivation, what I just did the proof. I did that just out of anyone's interest, but you might be asked to give that proof. Not necessarily you don't need to remember the proof, but there might, in exam question, might kind of guide you, but you could do something similar to what I've done here, but you don't need to know the proof, but you do need to know these 5 log laws. Okay, these 3 are the main 3 though, I will say, okay, but you need to remember all 5. These 2 at the end are just like special cases, okay, but you need to remember all 5 of them, particularly the first 3. Exam questions, an exam paper, you will very often be asked questions involving these log laws, so you must remember them, and we will be going over a bunch of questions now. So that's really essentially it. So these 5 log laws, and you need to remember that for every log, my input P and Q, they both have to be positive, okay? My inputs in my log, my P and Q, all have to be positive. That's what we looked at the start. And also my base A has to be positive as well. But also A cannot be 1. This is all you need to remember, okay? Okay, looks like a lot again, but we're going to put these in action. It's kind of like with trig identities. You need to know your trig identities, and you can use that to do sort of to show certain equations, right? It's the same sort of idea here. So let's have a look at some questions then with these log laws. So we need to write as a single logarithm log of 3 to the 6 add log 3 to the 7. And okay, as a single logarithm, I notice I'm adding one logarithm with another with the same base. So if I'm adding 2 logs together in this way, I can combine them. Because I'm adding them, I'll be multiplying them. So log 3 of 6 times 7, and that will be log 3 of 42, and that's 1 log. Part B, log 2. In fact, I'll write it here actually. I'll write the log laws here. Log A of P add log P of Q equals log A of PQ. Log A of P take away log P of A of Q equals log A of P over Q. And also log A of P to the N is N log A of P. These are the 3 main ones. So what I used in the first example was this top one here. Okay, if you add 2 logs, you bring them as 1 and multiply them. Okay, part B, we have log, I'll do it down here, log 2 of 15 take away log 2 of 3. So if we're taking away 2 logs, we're going to be using this second one here. So as a single log, that's log 2. We're going to divide the first 15 by the bottom 3. Divide the 2. So if we do that, log 2 of 5. Okay, 15 over 3 is 5. And that is my answer. Part C, we now need 2 log of 5 of 3. Add 3 log 5 of 2. Now, what we again, you notice I'm adding the 2 logs, so I will be using this top log law here. So I'm going to bring them I'm going to times them together effectively. But I can't do that at the moment because, again, stare at my log laws. There's no coefficient in the front, right? What I have here in part C is 2 lots of log and then 3 lots of log. I only have 1 log and 1 in all the logs. So if I have different amounts of logs that are coefficient, if you will, a coefficient, I basically, you need to account for that, right? So how am I going to get rid of the 2 and the 3? Well, this is where we can use the third log law. And actually, because we have a multiple, right, we have a coefficient, a number outside the log, I can bring it in as a power. So firstly, 2 log 5 of 3 would be log 5 of 3 to the power 2. So the 2, again, if it's a number outside, can then become a power inside the log via this log law here. So make sure that made sense. Make sure you understand that. And then likewise, then if we add 3 log 5 over 2, that's if we bring the 3 as a power inside, that's log 5 over 2 to the 3. Now we've got rid of the coefficients, and they're just single logs. Just a coefficient of 1, right? Well, actually, I can simplify it first, what I've got. So 3 squared is 9. And then 2 to the 3 is 8. Now I can use the first one here. Right, I can use the first log law here. So then that would be log 5 of 9 times 8. Okay, bring them together and times them, because I'm adding. So then 9 times 8 is 72. So that's log 5 of 72. And that is my answer. Part D, probably have to do it up here. We need to find the log. Well, we need to find log 10 of 3. Take away 4. Log 10 of a half. Okay. So firstly, log 10 of 3 is fine. There's no number in the front. But there's a number here of minus 4. Well, 4, right? This log, 4 log 10, this 4 is a problem. I need to get rid of the coefficient. So how can I do that? Again, I could bring that power inside the log. So that'd be log 10 of 3. Take away, then log 10, the 4 is a power. So the half is all raised to the power 4. And then we could just simplify. We could simplify half to the 4. A half to the power of 4 is 1 over 16. Right, you just put that in your calculator if you're a bit unsure, but there we are. So that's log 10 of 3. Take away log 10 of a 16th. Now, again, I've got singular logs now, no numbers in the front. So I can, I'm subtracting. So I can apply this second log law here. So I'm going to divide the first by the second one. So it's log 10 of 3. 3 divided by a 16th, right? Divided by the second log. If I do 3 divided by 16th, that would be, if we put that in the calculator, say, 3 divided by a 16th, that is 48. The log 10 of 48. There. Okay, so there we are. So that is the whole essence of this little subchapter here. Just applying these log laws. Okay. So yes. So again, once you get used to it, once you practice enough questions, they'll become second nature. These log laws. But there we are. Okay, in the same sort of vein, we're going to need to simplify these expressions. So it says write in terms of log a to the x, log a to the y, and log a to the z. Okay, so again, what I'm going to do, just to help, I'm going to rewrite the power laws. So a to the p add log a to the q is log a of pq, and then log a to the p take away log a to the q is log a, and then p divided by q, and then log a to the p to the what was it, p to the n is n log a of p. Okay, those are my 3 log laws, so I'm going to use them here. So firstly, we have log a to the x squared yz cubed. I only want my answer in log a x, y or z only. I've got x squared yz cubed. So it's a bit different, right, than just x, y, z. So, firstly, I can split up a log, okay? So remember, I can always go both ways with these log laws. I can go either equation. So here, because I've got a multiple, I've got a product in my log, I can split the logs up. I can create several logs added together with the same log laws. So that would look like, if I split up the product, that'd be log a of x squared, then log a of y, and then log a of z cubed. Okay, hopefully you're happy with that. So I've got a product here, and I can split each part, so the x squared, the y, and the z cubed, into all different logs by adding them using this power law here. Hopefully that made sense. So at that point, to get it in terms of just x, y, and z, well, y, that's cool, log a y, but I've got z cubed and x squared. I don't want squares or cubes, no powers. How can I get rid of the power, if you will? I can bring the power to the front. So then that, using this log law here, so then that will go to 2 log ax, add log ay, add 3 log az, and now these are in terms of log a, x, and y only. Cool. Part B, we have log a of x over y cubed. And so notice I've got a division inside a log. I can again use the second log law. If I've got a division, I can split up the log as log a of x, take away log a of y cubed. Okay, I can split up a division by subtracting one log from another. Okay, and so, well, log ax, that's cool. That's just log ax. But I need y cubed here to just be y. So I'm going to get rid of the power 3. I'm going to move it to the front using the third log law here. And that would be 3. Take away 3 log a of y. And there we are. Part C, we have log a. Oh, we have log a of, what was it? X root y over z. Yes. So again, what we can do is, I've got a division, right? I've got a fraction, a quotient in a log, so I could split that up. So the numerator of log a of x root y, then take away the bottom of log a of z. And so here, well, I've got log a z, that's just z, that's cool. But here, I've got x root y. So I'm going to need to further split this up. Okay, well, again, I've got a product, so what I can do here is split up this log to say that it's log a of x add log a of root y, take away log a of z, and then, well, that'd be, well, lastly, well, I've got log a x, cool, log a z, but log a root y, I can only have a log of y, okay? This root I need to take care of. Wow, if we remember our powers, our indices, we know that root y is just from y to a half. Well, hang on, now we've got a power, we can bring the power to the front. So then we can say log a of x, add a half log a of y, take away log a of z. And there we are. Cool. Then part D, I'll make some room here. Okay, so we need to simplify for part D. Log a of x over a to the 4. Alright, so firstly, again, we've got a quotient, so we can split up the division as log a of x, the top part, take away the bottom part of a to the 4. Well, that's log ax, that's cool, that's great, log ax. But log a of a to the 4, well, firstly, we can move the 4 to the front, so that's going to be minus 4 log a of a. But remember this, log a of a, remember that was another log law we saw up here. Log a of a would always equal 1. Okay, so you need to remember that. So log a of a would equal 1. So that's effectively going to be log a of x, take away 4 lots of 1. So let's just take away 4. And there we are. There we are. Cool. So hopefully you're starting to get a bit of a gist now, sort of a groove for using these log laws. Okay, and also we can solve equations using logarithms, using these log laws as well. So if we've got an equation involving logs, we can solve it now using log laws to simplify it. So, okay, so we need to solve this equation. Log 10 of 4 add 2 log 10 of x. So we need to solve for x, right? And this is all equal to 2. Solve for x. So, What we're basically going to do is we basically need well, firstly, what we need to do is combine all the logs as one. Okay. Well, firstly, again, I got a coefficient of 2 in this log here. In order to apply log laws, I need to get rid of a coefficient. Okay. So the coefficient needs to come as a power inside. So that would be log 10 of 4. Right, log 10 of 4 add log 10 of x. And that'd be x squared, right? Power of 2. Because the number 2's come as a power inside. That's equal to 2. And so actually now we can bring it as a single log. Because now we can, because it adding the 2 logs, we can multiply it inside. So log 10 of 4 times x squared. Right, and that's equal to 2. Now at this point, there are two things you can do here. To solve for x, what you can do is you could either I'm not even going to call them methods actually. 2 little things you can do to solve from here is, firstly, you could just convert it into a log. An exponential, sorry. So if you converted this back into exponential form, so remember that's saying the base of 10, which is by power of 2, 10 squared is what I've got inside the log of 4x squared. Now, this is an equation I can easily solve at this point. So 10 squared is 100. So 100 is going to be 4x squared. So x squared is going to be 100 divided by 4, which is 25. So x is going to be plus or minus root 25, which is 5. So plus or minus 5. Okay. What you could also do, alternatively, is if you're a tad bit unsure about how to convert into an exponential, what you can do instead, we can make both sides into a log. So obviously we've got the left side as a log already, but 2 isn't a log. We can make it a log though, because what we can say, so log 10 of 4x squared, we can make a number a log by using the power law here. So what we can say is the power law, but what we can do is use this log law here. So we've got the base a as the same as my actual input in my log. Okay, so what do I mean by here? So what we can do effectively is where is it? What we can do here is to convert 2 into a log, right, using my power laws. I can say that's log the same base 10, so always has to be the same base of 10. Then I can say, quite craftily, I can say that's 10 squared, okay? And so what I can do here, hopefully you recognise why that's allowed, because if I had log 10 of 10 squared, but I moved the 2 outside to get 2 log 10 of 10. And so then remember the log law, if I got the same base as my input, that will always equal 1. So it's 2 lots of 1, which is just 2. Okay? Now at that point I've got 2 logs on either side. So what I can do here at this point instead is actually say that my input, because the bases are the same, the only thing different are the inputs. So I can say the inputs are the same. So I can equate the inputs. The 4x squared is 10 squared. Well, at that point, that's just what we got that way. Okay. And then obviously you'd get the same roots as x is plus or minus 5. Okay. So you can do either or. So you can convert this into an exponential like I've done here. Or if you're a bit unsure, you can just convert the number as a log in its own right. Okay. By making a log of the same base. Now, those are my 2 possible solutions, right? You should always check if you've got multiple solutions, which if you can accept both of them or which ones you can't allow. So firstly, if x is 5, well, if x is 5, well, what you could do is just plug it into the equation and see if it makes sense. You could do that. I'm not going to do that here because I can just quickly spot that actually if obviously we have a solution, it must be defined, right? Now think about what I said at the start, is that every log base a to the b has to be positive, right? B has to be positive. Every input, everything inside the log has to be positive. Well, here in my equation, I got log of x. So that means x has to be positive, right? So that means x has to be positive. So without having to check manually putting into the calculator if you're unsure, I could just spot that x has to be positive because x has to be inside the log for it to work. So x must be positive, so x can only be positive 5. If x is negative 5, if you were to try all that, what you'd have is log here, if you put in x is minus 5 here, you'd have 2 log 10 of minus 5. That will not be defined. You would get it would say math error or undefined, effectively, right, in your calculator. So that would not be a solution, because of the whole idea that in the log, as we discussed, your input can only be positive. Okay, it must be positive. So there we are. Okay, we can solve another equation. So here we have log 3 of x plus 11 take away log 3 of x minus 5 equal to 2. So again, I need to convert. I need to combine everything as just one single log. So what I can do here is, well, obviously there's no numbers in front. That's great. So I'm subtracting 2 logs. I can divide them. So log 3 of x plus 11 divided by x minus 5, and that will equal 2. And so at that point, what you can do again, you could either just compare, no, you could convert it into an exponential, because then the base is 3, base of 3 to the power of 2 equals what I've got inside, x plus 11 over x minus 5. But at that point, we can solve this fraction. Alternatively, I could convert this into a log in its own right. So 2, I can say, is 2 log of the same base 3. Then it has to be 3 as well. That will go to 1. And then I can bring the 2 inside the log to be log 3 of 3 squared. And so at that point, because I've got 2 logs on either equation, that means the inputs have to be inside the logs have to be the same. So therefore x plus 11 over x minus 5 equals indeed 3 squared. Okay, at that point I'm going to solve. So 3 squared is 9. And so if I just cross multiply, x plus 11 is going to be 9 lots of x minus 5. So x plus 11 is 9x minus 45. And so if I solve for x then, I would get that, if I take away x on both sides, I get 11 equals 8x minus 45. So 8x, if I add 45, is going to be 56. So x is going to be 56 divided by 8, which is 7. And so there we are. So that is my solution to that equation. X is 7 only. And that makes sense, because if I were to plug x is 7 into all my logs here at the start, x plus 11, that'd be 18. Right? That'd be 18. That's positive. X minus 5, 7 minus 5 is 2. That's also positive. So that it's all defined. It's all well and good if we take x is 7. So that is a legit solution. And so there we are. So that is that. Okay, so what I want to do now is just do a bunch of more practice questions. We're going to look at a bunch of exam questions in a minute, because again, a very important topic this is, comes up all the time. Very important. Once you get the hang of it, it isn't too bad in my opinion. But there we are. So here we are given that log 3 of x plus 1 equals 1 add 2 log 3 of x minus 1. We firstly need to show that we need to get to this quadratic here. Again, pretty random, but I always say just try and do what you can do, right? So here I can probably simplify it by using log laws, and then I might end up with this equation here. Let's just see what we can do. So firstly, I'm going to bring all the logs to one side. So I got this 2 log 3 of x minus 1. I'm going to bring it to the left by subtracting by 2 log of that. So if I do log 3 of x plus 1, take away 2 log 3 of x minus 1, that just leaves me 1. So the idea is all the physical numbers with no logs on one side and all the log terms on the other. Because now I've got all the logs, I can combine them as one single log and solve them there. So again, if I'm subtracting, I'm going to divide, right, the x plus 1, x minus 1. I'm going to divide the two logs, but I have a 2 in front. That's troublesome, right? I only want singular logs, just 1 in front. I got 2, so I'm going to bring it as a power. So log 3 of x plus 1. Take away log 3 of x plus 1 minus 1. That'd be squared then, because the power would then be 2 equal to 1. Right. And then at that point, now I can divide. So log 3 of x plus 1 divided by x minus 1 squared equals 1. And so actually I can be a bit crafty and then say that 1 is just 1 log base of 3, the same base, 3, and then 3. Okay, because then that cancelled to get me just 1. And then I can bring the 1 inside, so that's log 3 of 3 to the power of 1. Well, that's just 3. And so that at that point, if I compare what's inside the logs, that means that x plus 1, I'll do it up here actually, x plus 1 over x minus 1 squared equals 3. Okay? So hopefully with me there. At this point, it's just no longer logs, it's just solving an equation. So at that point, I can cross multiply, so x plus 1 is 3 lots of x minus 1 squared. But then I need to expand it, right? So x plus 1 is going to be 3 lots of, well, x minus 1 squared is x minus 1, x minus 1. And you should be able to expand that to get x squared minus 2x add 1. So that'd be x squared minus 2x add 1. So then that'd be x plus 1 is 3x squared, take away 6x plus 3. And so if I move the x plus 1 to the other side, subtract by it, I get 3x squared, take away 7x plus 2 equal to 0. And what do you know? That's the quadratic I end up with. Cool. There we are. I'm on the right track. Then part B says, hence or otherwise solve the log equation. Well, solving the log equation corresponds to solving the quadratic that we just got, right? So if I solve it, just to show my full working out, I can just state the quadratic formula. So that'd be 7 plus or minus the root of minus 7 squared, take away 4 lots of 3 lots of 2 over 2 lots of 3. And so that will get me x is 2 or x is a third. So those are my two solutions for x, but especially with logs, you must always double check your answers, because at least one of them might not be valid. And so to check my solutions, I'm going to check each solution with to make sure every log, the original log, is defined. So firstly, we had x was 2. X is 2. That's my first solution. Is that valid? Can it happen? Well, x plus 1 in this case, x plus 1 would be 3. That's positive. That's great. X minus 1, that would be 1. That's still positive. Cool. So x can be 2. What if then x is a half? Well, then if I plug a half into each log, I'd get a half add 1, that's 1.5. And then a half minus 1, that's negative 0.5. That's a negative. So x cannot be a half, right? So I'm going to say, but x cannot be a half. A third, my apologies. It's still the same thing, right? If I plugged in a third instead, my apologies, that would be 1.33, and this would be minus 0.66. Still negative, okay. My apologies. So x cannot be a third as log, log of 3 to the x minus 1 equals log 3 to the a third minus 1, which is log 3 of negative 2/3, which is undefined. So that means my only solution is x is 2. So it's imperative to always check all your solutions with the logs to make sure every log is defined. Okay. Okay, let's move on to some exam questions now. So here we are told that a, the value of a, is log 2 to the x, and b is log 2 to the x plus 8. So what we need to find is, in terms of a and b, these two logs specifically, we first need to find the log of 2 to the root x. Well, root x, again, there's no roots, but I can convert a root into a power by saying log 2 of x to a half. Then I can bring the half to the front to then say a half log 2 of x. Well, log 2 of x is a, right? So that's a half a. And there we are. Part B, we need to say log 2 of x squared add 8x. So it's not really apparent what we can do. What you cannot do, okay, very common pitfall. You might think we're adding, so you can say what, log 2 of x squared add log 2 of 8x. That, remember, that cannot happen. When we're using the addition law, the addition has to be outside the log, right? But when we're inside the log, if we're adding inside, that we can't do anything to that, okay? Only adding two logs together. I just want to make that very clear, okay? We cannot use the addition log law at this point. So there's not much we can do, but what we can do is actually notice I can factor an x inside. X is common. So if I factor an x, I can say x of x at 8. Now I've got a product inside my log, and now I can use the addition law, because I can split up the product inside as the logs log 2 of x add log 2 of x plus 8. Well, hang on, log 2 of x is a, right? And log 2 of x plus 8 is b. So this is just a add b. And there we are. Okay. Part C, we need to find log 2 of 8 add 64 over x. Right. So again, I notice I have a division here, but that's kind of affected by the adding 8. So what I can do is just add the two parts. I can combine this as one fraction. Okay, because remember 8 is just 8 over 1 effectively. So if I do that, then if I do it somewhere here, 8 over 1 add 64 over x. Well, I need to multiply the first fraction by x to get 8x add 64 over x. Okay, so hopefully you recognise I can simplify what I've got inside the log as this single fraction here by adding the two fractions together. So at that point I get log 2 of 8x add 64 over x. Now I've got an overall fraction in 1. So now I can split up the fraction by subtracting. So log 2 of 84 add 8x add 64. Take away log 2 of x. Okay, so here again, remember I'm going to need to simplify this, because I either need log of x or x plus 8. I've got neither here. I've got 8x of 64. But again, what I can do, there's nothing I can't apply any log laws at the moment, but I can again factorise here. So I can factorise to say log 2 of 8. I can pull an 8 out. 8 of x add 8. And then take away log 2 of x. That's just a. Okay, that's A. That's great. And actually then, I can split up the product in this log to then say log 2 of 8, add log 2 of x plus 8, take away A. Well, actually then, this is B. So this is B, take away A. But what about log 2 of 8? Well, actually, there's no unknowns, there's no algebra in there. What you could do is just put that in the calculator and you would get 3. Okay, so this is going to be 3, add B and take away 8, okay, as my final answer. Or you could realise that log 2 of 8 as an exponential, if this equals some value of x, then as an exponential, this is 2 to the power of x equals 8. Well, 8 is 2 cubed, hence x is 3. Hence we get 3 here. But honestly, probably in exam situations, probably better to put it in the calculator very quickly to get the answer 3. So there we are. Cool. Right. Okay, now we've got another sort of an equation question. Very similar to what we just did. So we're given that log of base 2 to the x plus 3, add log 2 to the x plus 10 equals 2 add 2 log 2 of 10 of x. So again, I need to get to this random quadratic, okay, but it's not so random, but it looks random at the moment. Again, I'm just going to need to simplify as much as I can to get to that point. So firstly, my strategy is I want all the logs on one side because I just want a single log. So I'm going to move this 2 log x to the other side by subtracting. So we get log 2 of x plus 3, add log 2 of x plus 10, take away 2 log 2 of x equals 2. Okay, now I can combine them. Well, firstly, I can combine the first 2 logs. They're just singular logs, no number in the front. I'm adding them, so I'm going to times them inside. So this is log 2 of x plus 3 times by x plus 10. Then I'm taking away this log here, but I have a 2 in front. I only want logs on their own, no numbers in front, so I'm going to bring it as a power. So log 2 of x squared equals 2. And then I can divide the 2 logs here. So these 2 logs, I'm subtracting them, so I'm going to divide one by the other. So log 2 of x plus 3, x plus 10 over x squared. And then I'm going to use a big bracket here to signify this is all inside the log, and that equals 2. Right, and so then at that point, again, I can convert this straight into an exponential form, but if you're not able to recognise that, what you can say is, I need to make the right side a log as well. I need to make it another log. So then I can say it's log 2 log 2 of 2, because that would get me 1, right? So I'm just timesing by 1 effectively. So then I can bring the 2 inside this log to get log 2 of 2 squared. Well, that's 4, right? Now both equations are the same. So inside both what's inside the logs are the same. So therefore, x plus 3, x plus 10 divided by x squared equals 4, right? And so at that point, I could cross multiply to get x plus 3, x plus 10 equals 4x squared. And now you can hopefully see a quadratic equation is going to emerge. So if I expand this, I get x squared, add 10x, add 3x is 13x, add 30, and they're going to take away the 4x squared equal to 0. Then if I simplify this, I get minus 3x squared, add 13x, add 30 equal to 0. But I don't like a negative in front of my x squared, so I'm going to times or divide by minus 1. It's the same thing. I'm going to flip all the signs to get 3x squared minus 13x minus 30 equal to 0, and that should be what they've got. Yes, great. Then it says for part B we need to write down the roots. So when it says write down, I don't need to show any working. I can just use my calculator directly to just get me the roots. I just need to write the roots down. So if I do that, then put that in a calculator, the roots are x is equal to 6 or x equal to minus 5 over 3. Okay, so those are the roots. Probably the easiest mark in an A level, but there we are. Then it says, hence state which of the roots we found is not a solution, given a reason for your answer. So again, it's that checking, right? So we've got two solutions. Which one isn't a solution? We need to check the logs. So firstly, if we had x is 6, if we plug that into every single log, right, originally, into these three logs here, but firstly, x plus 3, that'd be 6 add 3, that's 9, that's great, that's positive. 6 add 10 is 16, that's positive, and x is 6, that's positive too. Great, that actually can be a solution, which means the other solution, x is, what was it, minus 5/3, probably isn't going to be the right one. And immediately you can spot here that I have x. So if I put x is minus 5 over 3, that's negative. That cannot happen. That's not defined. If you put log of minus 5 over 3 in your calculator, that won't work. So that is the wrong root. So x is minus 5 over 3 is not a solution because the log, what was it, log of 2 to the x, that's going to be log 2 of minus 5/3 is undefined, as logs can only take positive values. Or positive inputs, right? And there we are, or positive values of x, whichever you want to say it. But the point is we can't have a negative inside the log, so that cannot happen. Cool. Okay, again, we've got another equation. We need to solve this equation now, just 5 marks, just solve it. So we have 2 log 5 of 3x minus 2, take away log 5 of x equals 2. So again, all the logs are on one side. I need to put this all as one log. But I'm subtracting the logs, so I'm going to divide them. But before I do that, I notice I have a 2 in front here. I need to put that as a power. So then that'd be log 5 of 3x minus 2 squared. Take away log 5 of x equals 2. Now I can bring it as one log by dividing. So that'd be 3x minus 2 squared over x, and that will equal 2. Okay, and so then at that point, I can then convert the whole thing here as an exponential, or say that 2 is actually just 2 log base 5, again the same base, of 5 then, right? That will get me 1, but actually what I can do then is bring the 2 as a power, so log 5 of 5 squared, which is 25. And so then if I compare the two logs, that means what the inputs, so 3x minus 2 squared over x, has to equal 25. And so then I can cross multiply to get 3x minus 2 squared equals 25x. Then if I expand this bracket here, that would be, I'll do it somewhere here, that would be 9x squared, take away 6x, take away another 6x, so 12x, add 4. So 9x squared, take away 12x plus 4, and then I'm going to move the 25x to the other side to set it to 0. Now I've got a quadratic, so 9x squared, take away 37x, add 4 equals 0. And so at that point I'm going to use the formula, so x is going to be 37 plus or minus the root of minus 7, 37 squared, take away 4 lots of 9 of 4, divided by 2 lots of 9. And so that would be, if I put that in the calculator, I get 4 or a ninth. Those are my two roots, but I need to check as well, right? Firstly, x is 4. So if I look at this original log then, if I try x with 4, see what happens into each log. Well, 3x minus 2, well, 3 lots of 4 minus 2, that'll be 10. So my input will be 10 if x is 4 here. That's positive, that's great. And my x is 4. So that's positive clearly. So that has to be a solution. The other solution was a ninth. Okay. So if I input a ninth into 3x minus 2. So if I do 3 lots of a ninth. So I'll do it here actually. 3 lots of a ninth, take away 2. In my calculator, I get minus 5/3. Oh, that's a negative. That'll give me a negative log. That cannot happen. Cannot be a root then. So I'm going to say, but x cannot be a ninth as log, what was the log? Log 5 of 3x minus 2 is equal to log 5 of minus 5/3, which is undefined. As logs cannot be negative or cannot take negative inputs or negative values. Okay, so therefore x can only be 4. That's my only solution there. Cool. There we are. So hopefully you really are starting a good picture now how we can use logs, the log laws to simplify and to solve equations. Okay, so I've got this trickier exam question here. Really makes you think, this question does, especially part B. But let's have a look. We were told that A is greater than B is greater than 0. Alternatively, you could flip that and say 0 is less than B is less than A. Okay, either or. And we're given that log of A minus log of B is log of A minus B. Now, they haven't given me the base here. I will touch on that more in another video, but that doesn't really matter. It could be any base, effectively. But I'll talk about that later on. Okay, we need to show this. So firstly, I'm given an equation. Again, if I'm going to get this random formula here, again, let's just try and see what I can do. So I can maybe use log laws. Well, firstly, I have 2 logs here. So I can, if I'm subtracting the logs, I can divide them. So I can say log of A divided by B is equal to log of A minus B. And so therefore A over B is A minus B. Okay. And so then I can multiply by B. So cross multiply, get rid of the fraction. So A is B lots of A minus B. If I expand that, I get A is AB, take away B squared. Now, I want to rearrange for A. So I need to sort of get A on its own. So if I move AB to the left, I get A take away AB is minus B squared. So if I factor an A out, that'd be A of 1 minus B equals minus B squared. And so then if I divide by 1 minus B, I get A is minus B squared over 1 minus B. Now, it's pretty much the same, but notice there's no negative, but also it's B minus 1 on the bottom, not 1 minus B. But actually, I can just squeeze in the negative. I can squeeze a negative into the bottom and say that this is B squared over minus lots of 1 minus B. And actually then, if I expand that negative on the bottom, I can say that A is indeed B squared over minus 1 plus B, so B minus 1. And that is it. There we are. Part A. Cool. So part B then says, write down the full restriction on the value of B, explaining the reason for this restriction. So, okay. So, what that's saying is, what values of B can you have? And what values B can't you have? So it's kind of asking for like the domain. Again, not talked about the start really. But, well, firstly, all the logs have to be defined. So that means A has to be positive. Well, we're already given that. A is above 0. That's in the inequality. So that's cool. B has to be above 0. B has to be positive as well. Again, we're given B is greater than 0 here. But also, A minus B has to be greater than 0. So that means if A minus B is greater than 0, positive, that A is greater than B. Well, actually, we're given that as well. So actually, nothing new there. Okay, that's great. So really, we need to stare at this formula here. So using the formula, what values of B can't we have? Well, the first one probably strikes to you, perhaps. I'll do it here, actually. The first value is that B cannot be 1. Because simply then, if B is equal to 1, the fraction isn't defined. So I'm going to say B can't be 1 because if B equals 1, then A equals 1 over 0, which is undefined. Because then you divide it by 0, right? However, that's not the full restriction. That's just that's one part of it, but that isn't the only bit. You probably pick up a mark there, right? Now, the second thing is to realise that actually, if we look at this inequality again, that means A has to be positive, right? We've discussed this. A has to be positive. If A is positive and A equals this, then actually I'm going to say and the A, which is equal to B squared minus B minus 1, that has to be positive, right? Because that's A. A has to be positive, right? And so what that means then, if this fraction has to be positive, right? So I'm going to get rid of some of this now. This fraction B squared, or B minus 1, is positive. Now, B squared is a square number. That's positive by default. So B squared is positive as B squared as B. Yeah, no, B squared is a square number, right? So what this is saying is, effectively, what this fraction is saying is, I've got a positive number B squared, and a positive divided by something has to get me a positive, right? So if the fraction is positive, what that means is a positive has to divide by another positive, right? Because if B minus 1 is negative, then the fraction will be negative, but no, the fraction must be positive, as we discussed. So that means B minus 1 has to be greater than 0 as well, okay? The B minus 1 has to be positive, so therefore B is just greater than 1. And that is the full restriction, okay? And actually, that also incorporates that B cannot be 1, because if B is greater than 1, then B cannot be greater than equal to 1, okay? Because if it's equal to 1, well, obviously, as we saw, it wouldn't work. So B has to be strictly greater than 1, and that is the full restriction. And there we are. Okay, cool. I'm making a little note here. I'm saying that as A has to be positive. Okay, but there we are. That is the full explanation, and there we are. Okay. Yeah, it's one of those that looks very scary, like a bit like, what does this mean on first glance? But hopefully now that makes a bit of sense. But quite a tricky question that is. Okay, I'm going to leave off with this sort of challenge question from the book. To do with simultaneous equations. Could it be asked? Very unlikely, but it's a nice little challenge question to finish off on. So you have these simultaneous equations, A and B is 30, looks standard, but then we have a log equation. So log of 6 to the A and log 6 of B is 2. And so we need to solve these simultaneous equations for A and B. So firstly, I think that when you got an unusual simultaneous equation like this, it's probably best to just rearrange and substitute. So if I call this 1 and 2, I can rearrange the top one to say that A is 13 minus B. And so at that point, if I substitute that into the second one, I then get log of 6 to the A, which is 13 minus B, add log 6 of B is 2. And so at that point, I can use log laws, right? Because I'm adding the two logs, I can combine them as one, multiply them, so I get log 6 of 13 minus B times by B is equal to 2. And so then I can expand the bracket firstly, so log 6 of B 13B take away b squared, that equals 2. Now at that point, okay, that's just solving this equation, so I can convert that into an exponential, or convert this 2 as a log to say 2 log of 6 to the 6 to keep the base the same, so that log will go to 1, but instead I can say that's just log 6 of 6 squared, which is 36, and so the 2 logs have to be the same, which means that 13b minus b squared equals 36, and so we got a quadratic, so I've got b squared minus 13b add 36 equals 0, okay? And now, to solve this quadratic, so b is going to be 13 plus or minus the root of minus 13 all squared, take away 4 lots of 1 lots of 36 over 2 lots of 1, and so that would get me that will get me b is 9 or b is 4. Okay, but I need to check if these solutions make sense. Again, I need to check if they are valid, so I need to check it into each individual log up here, right? So if I firstly check if b was 9, then 13 minus b here, 13 minus 9 would be 4. That's positive, that's great. And b would be 9, that's positive, great. So that makes sense. And then if b is going to be instead 4, my other root, then 13 minus b here, that's 13 minus 4, that'll be 9. And b would be 4. So actually both are valid in this case, okay? Cool. So there we are. So both of these solutions can happen. So then that's my value of b. Then simply to get the a, well, we know a is this, right? We know a is 13 minus b. So a is 13 minus b. So therefore if b is equal to 9, that means a is going to be 13 minus 9, which is 4. And then if b is equal to 4, then a is 13 minus 4, which is 9. Okay. So a is so we've got the solutions: a is 4, b is 9, or if a is 9, b is 4. Okay. But we're told the positive. That's great. They're all positive. But we're given this little caveat as well. A has to be positive. A has to be bigger than b, greater than b. So, but a has to be bigger than b. But actually look here, in this first pair, a is 4, b is 9. Well, that means 4 is less than 9. A is less than b here. So we can't have that. So the only solution we can have is a is 9, b is 4 only, because then 9, a is greater than b, because 9 for a is indeed bigger than 4. And so that's my only solution there. Okay, cool. So that's it then. So that's log laws. So yes, we'll be delving a bit deeper. I'll be looking at solving more types of equations next time. But for now, hopefully you just know how to apply the log laws, and these questions have helped. But yeah, I'll see you next time.